Hello and welcome to the second section of the Mastering Keras course. What we're going to be doing in this section is working with the Keras functional API. We're going to use the functional API to go through and produce a variety of basic neural network models, things like MLPs, multi-layer perceptrons, convolutional neural networks, recurrent neural networks, in particular LSTMs, and a denoising autoencoder. Now, some of you are probably familiar with these sorts of models, so the idea is to give you a chance to see how to use the functional API to build them. We'll also just review a few different topics that will be helpful, some tricks, some tools that you can use in deep learning, just to try to get everyone on the same page at the same level before we head on to the more advanced models and advanced deep learning techniques that will be looked in the other sections of the course. So this video is about MLPs, and we're going to be using them for simple data analytics. What we're going to be paying attention to in this video and the code script that goes along with it is, of course, using the Keras functional API for defining models, but we'll also spend a little bit of time talking about implementing regularization, implementing batch normalization, and working with validation data and early stopping. Now, like I said earlier, some of you are probably familiar with these things, so if you are, you can skip sections here quite happily. Those of you who want to review this or are perhaps seeing it for the first time, this is for you. Let us open the Module 2.1 Jupyter Notebook. So here we are in the Module 2.1 Jupyter Notebook. This is the first time we're really using the Jupyter Notebook, so I'll spend a little bit of time talking about it. You'll see at the beginning of each of these notebooks, there'll be a little overview of what we're doing. Then we'll import all the required libraries, and then we'll jump into things. So in this notebook, we're going to be building a MLP, a multi-layered perceptron. We'll be using the Keras functional API, but we'll start off by doing the sort of basic version of this, using the sequential approach that some of you may be familiar with, doing the sort of simplest thing we can, and then we'll see how we can improve it in various ways. The first way will be by using the functional API, but we'll also implement some regularization, some batch normalization, work with validation data, and early stopping. Now, we're going to be working with a simple data set known as the Boston housing price data. This is a regression problem, so there is a bunch of input variables, and the target variable is a real valued number that we want to predict. So let us do the imports, let us get the data. Okay. We have the data. Now, this Boston housing data is a very commonly used data set in data science. You can get information on it from, for example, or just Google it, but here it is on cstoronto.edu. The variables we're looking at, various characteristics of different environments. These are the input features, so things like per capita crime rates, proportion of residential land zoned for lots over 25,000 square feet, etc. And the target variable we want to predict is the median value of owner-occupied homes in the region. So that's what we're going to be working with. What we're going to do at the beginning is produce a very basic implementation of an MLP. It's going to be a very basic depth network. It's going to be a very basic architecture that we're working with, but it's also going to be a very basic training algorithm. We're not going to do anything clever here. And so this is not an approach you want to replicate. It's an approach we're going to use as a basis to look at how we can improve things. And here we define a function called defineModel1, and this looks at the basic sequential approach for doing a simple multi-layered perceptron for this data. We create the sequential model and we go through adding layers to the model. We add 2 hidden layers, both of them are ReLU activated. One has 14 units, one has 6. Simple as can be. We of course have a linear output layer because it's a regression problem, and we return the model. We can then define our model and compile it. We're just going to use a basic Atom optimizer. You can of course play around and improve things, but don't do it on this component of the notebook because this is our simple implementation that we're going to improve. We're going to use mean squared error loss, and we can get a summary of the model. There we have it, the layers involved, the number of parameters, and then we fit the model to the training data. Now, I've already done this here. Run it for 1,000 epochs. It will run very quickly. It's a small data set. And if we have a look down here, we now have a little function that will allow us to plot our training history. And when we plot it, we get a graphical representation of mean squared error after each epoch of training on the training data. And of course, it's on the training data. This is only going to get better and better. The model will fit closer and closer to the training data. I mean, it's noisy, but the trend will be better and better and eventually leveling off. Right, then we want to see how well our model performs on the test data. Here's a little test model function, and here we go, a mean squared error of 152. Now, as I said, this is a really basic implementation. There's lots wrong with it. So let's think of some of the things we can do to make it more reasonable. The most obvious is we shouldn't be just looking at how well a model does on training data when we train it. We want a model that we can go on to use to apply to new data. We want the best model that we can get in terms of how well it will perform on new data, not on training data. So we typically use validation data. This is data not involved in training the model, not involved in fitting the model parameters, that we can see how well the model performs on this new data. This is just going to improve on the training data, but it won't improve on validation data. Eventually, the model will start to decline in performance on new data. That's when it starts to overfit on the training data. And it's at this point we want to stop training. We want to train while we continue to improve on validation data and then stop. So that's the obvious thing we have to change. We need to incorporate validation data and early stopping. We also would like to work with regularization. Regularization controls the complexity of the model. And this is extremely important. Deep neural networks are statistically complex models, and so they're prone to overfitting. By introducing regularization into your models, you can control or reduce this complexity and make the model less likely to overfit. So it's extraordinarily important to get used to working with regularization, and we'll introduce a form of regularization into our model now, and we'll talk about some other forms that we'll see in the next few videos. We'll also talk about batch normalization, and most importantly for this section, we'll see how to rewrite our model specification, our model definition, so that we end up using the Keras functional API instead of the sequential approach. Now that's really important because later in the course we're going to look at models that include, for example, multiple input and output layers or shared layers between different models, and we're simply not going to be able to do that sort of thing with the sequential approach. We need to get used to using the functional API. You'll find it's quite easy to use, but a lot of people start off just using the sequential approach. So our first change will be to actually use the functional API instead of the sequential model. And this is what it looks like. You see, we start off by defining our input layer, and then we proceed through defining new layers that take as arguments. These layers are themselves functions that take as argument the layer that goes into them. So here's our input layer, here's our first hidden layer, our second hidden layer, and our output layer. And then to put this all together, we use the model function, specify the input and the output. So our inputs is the input layer, our outputs is the outputs layer. And Keras, or TensorFlow behind it, can trace back the chain of the network chain that goes from outputs back to inputs and puts this all together into the model we're going to use. So that's the functional API. Play around with it. If there's things you don't understand, look them up. See if you can add some extra layers. The second thing I wanted to do is introduce regularization. So we talk a little bit about regularization here. It's a means of controlling the complexity of the model without changing its structure. And there's a few different common forms of regularization. L1, L2 regularization, which restricts the ability of model parameters to freely take on large values. Now, you may know L2 regularization as weight decay. That's a very common name for it in neural network circles. We can also constrain weights to have particular norms. We can do dropout, which restricts the ability of a model to tune parameters in a joint fashion. Every step of the training algorithm, it randomly drops out nodes from certain layers. And finally, noise injection. So we're going to see dropout being used in the next video. We'll see noise being added in the final video of this section. So at this point, let's add L2 regularization. We'll create a new version of our defined model function. The only thing that's going to be different is in the two hidden layers, we're going to introduce regularization. Kernel regularizer equals L2 with an L2 parameter. Here's our default L2 parameter. The larger this is, the more regularization occurs, which will create a model that is less statistically complex, less prone to overfitting. Now, of course, what we want to do is find the sweet spot where our model is as complex as can be without causing overfitting on the data we have. In reality, you'd want to tune this hyperparameter here. We're not going to do that, but you can, of course, do it as an exercise. So we've added L2 regularization to the 2 hidden layers. Third thing we'll look at improving is to add batch normalization. Now, what batch normalization is a technique which helps us to speed up the training process. What it does is it seeks to minimize the changes to the distributions that occur during the training process. Because, of course, we're training all the layers of the neural network at once. And as you tune a preceding layer, this affects its outputs to the later layers. And then the later layers have to adjust to this. Batch normalization seeks to minimize this effect of tuning preceding on later layers by normalizing the outputs of the layers. Now, we're going to add batch normalization after both of the hidden layers. There's a bit of a trick here because you actually have to add batch normalization between the layer itself and the activation function. So we now define our hidden layer, hidden 1. It's a dense layer that takes inputs, the input layer as argument. We've got our kernel regularization here. We don't specify an activation function because we want to apply batch normalization before the activation function. We also specify use bias to be false because batch normalization has a parameter inside it that will take care of the bias. So we set up hidden 1, but without an activation function with use bias equals false. Then we add a batch normalization layer, after which we then add the activation function layer that takes as argument the batch normalization layer. We do the same thing for the second hidden layer. So we now have batch normalization added to our network as well, which should speed things up when we're training. The final improvement we're going to do is work with validation data. We only want to keep training the model for as long as the performance on the validation data improves. So we need to keep track of that, and we'll add an early stopping callback. This is going to monitor the validation loss. It'll be looking at the mean squared error on the validation data after every epoch, and it will check to see that things are still improving. We give it a patience of 15. So if things don't improve for 15 epochs, we're going to stop the training. We say restore best weights equals true. So if things don't improve for 15 epochs, we stop the training and we restore the weights when the network performed best on the validation data. Right, now all we have to do is come back here and add this early stopping callback to our model fit call. We also, of course, want to actually have some validation data, so we add validation split here. Now, you have to be a little bit careful with this validation split. If your data is ordered in some way, this is going to take just a chunk off. So you should normally shuffle your data before using the validation split. Not shuffle here, but shuffle in your code preceding. So if we run this, I've already done that, of course. It's very quick, but even so, I've done it before. And we see, in fact, we stop at epoch 107. We said train for 1,000, but we stop at epoch 107 because at that point, validation data has ceased to improve. And we will restore the weights presumably from epoch 92 since we had a patient of 15. Now, if we look at our training data, we'll see here the validation data has already started to level off and is jumping around. So approximately here, we see that's probably epoch 92. That's the best performance on the validation data, and that's what we're going to restore. If we see how well a new model performs on the test data, we get a mean squared error of 129 compared to how the basic implementation performed on the test data, which was with a mean error of 152. So a little bit of an improvement. Remember, we're not working hard to tune hyperparameters here or tune the network architecture, so I've no doubt we could improve a lot more than that. And if you're interested, certainly it's a fun exercise to go and see how well you can actually make a deep learning model perform on this Boston housing dataset. Right, that's it for this video.